Next, we have, look, Bennett is going to talk about a thin plate approximation for fish floating.
I do need the mic.
Yeah. Chen? You have
Is
the
that
mic?
the mic?
Yes.
Great to have you all here in Adelaide. And thanks to Jordan for doing all the hard work in organising this meeting. So look, there's I've put a very obvious contradiction into the title of this talk, the thick, thin contradiction. The contribution of what I'll talk about is on how to apply a thin plate approximation to thick floating ice, like an ice shelf, whilst not completely abandoning the thickness of the ice. Here's a basic schematic of the problem. We've got an elastic body of thickness lowercase h, that's our ice shelf, which is floating on a fluid of depth capital H, that's our water cavity. Gravity is acting directly downwards. There's a horizontal length scale lambda, which is going to be a wavelength, and this is all in 2D. Use some standard assumptions, I won't go through them, and I will use the Navier equations to model the elastic deformations and Laplace's equation to model the fluid motions. So the Navier equation part is more complicated because it involves two unknowns as opposed to just one with Laplace's equation. So the goal here is to simplify the elastic part through some approximation. Now, ice shelves are, or can be, hundreds of meters thick, which is comparable to the depths of the water cavities on which they sit. But despite that, it is very common for myself and others to use to model ice shelves as thin elastic plates. And that is done on the basis that the waves in the ice are much greater in length than the thickness of the ice. And that's actually not too bad an assumption, because thick ice is going to transform waves which are, say, order 100 meters, like swell in the open ocean, into waves of length order kilometers in the ice. And what it means is that in this problem, we have a 1D elastic body, which is floating on the surface of a 2D fluid. And the effect of that is that the ice just changes the free surface condition at the top of the water cavity. And I think it's probably also worth noting that the model that we've ended up here with so far is exactly the same as the model that we would have if we had a sea ice cover rather than an ice shelf. Might sound a little odd. Now, the problem that we're actually going to solve is the one that's shown here. On the right-hand half of the domain, we have our ice cover, the ice shelf. On the left-hand side, we have open water. We send in an instant wave from the left. It's just going to have unit amplitude. And what we want to do is we want to then calculate the resulting motions of the ice and the water. Something looks a little wrong with this picture. Can anyone spot? Yeah, it's either way, but I prefer the most obscure way possible. Inherited that from my PhD supervisor. No one actually answered my question there, but I guess you all saw it. Yeah, okay, there's no submergence. We're using what we loosely refer to as the shallow draft approximation, where there's no submergence for the ice. Now, this approximation is very common in the sea ice literature, but it seems a lot more reasonable there because we're dealing with ice, which is maybe 1 meter thick, not 100 meters thick. One of the consequences of the shallow draft approximation is that the ice has a free edge. And that means that it's only experiencing fluid loading on its lower surface. Now, what we actually want to do is have an Archimedean draft, which is about 90% of the ice thickness. Well, I've tried to do this before during my PhD. My collaborator, Tim, also tried to do this during his postdoc. And we did it in the context of sea ice. And we both made a mistake, which is that we were applying the thin plate approximation from the very outset. So that means that we are taking this 1D solid body and then partially submerging it in a 2D fluid, which is a bit weird. And the result of that, one result of that is that the free edge conditions are maintained, but that is incorrect. And now that I'm looking at wave shelf interactions, I think that this is going to be important when you're predicting the stresses and strains close to the ice edge, because if you have a free edge, then the stresses and strains go to 0 there. I'm going to approach this problem using a variation principle, and I'll be using Cartesian coordinates, XZ, like shown here, and find all of the necessary interfaces, as you can see here. Don't need to worry too much about remembering them all. And then we're going to have 3 Lagrangians. There'll be one in the open water that you can see on the left, then one in the cavity, and one in the shelf. Okay, all right, now we come to the difficult part of the talk. Yeah, what shall I say here? My ideal number of equations for a talk is 0. The nature of what I'm presenting today is that, well, at least I don't have the skill to present it to you without showing you some long equations. I don't feel too well, on the basis of some of the talks we've seen, naming no names. I don't feel like I'm a complete outlier. Isn't that right, Noah? Yeah. But before I get into the nasty stuff, I want to give you some context so you can kind of glaze over for a few slides there and tell you about the novelties in the equations I'll be presenting you with. Because variation principles have been used for water wave problems for over half a century. And including by me during my PhD, but as I told you a few slides ago, I did it incorrectly. I derived the wrong boundary conditions. So in order to couple the solid ice to the fluid water, I'm going to be using a displacement potential, which is odd in the context of water waves. You would usually use a velocity potential. There's a lot of freedom that we put into the variational principle. So for instance, we are not assuming Bernoulli pressure from the outset. But from my perspective, the most important thing that we've done here is that we've removed the need for essential conditions. You might not know what essential conditions are unless you've worked on variational principles before. They are interfacial conditions that you impose external to the variational principle itself. Right? So the variational principle doesn't contain all of the physics usually. In this case, it does. So I'm going to take you through each Lagrangian. Each one is the difference between kinetic and potential energies. Okay, that's just standard. I'm going to start off with the ice shelf Lagrangian. And the kinetic energy. And at this point, you're going, well, what was all that fuss about nasty equations? Because this is straightforward. And really, the only thing to point out to you here is that I'm linearizing the domain. So we're just working on the equilibrium domain. By Shove domain, of course. And then we get to the potential energy. It's a lot more challenging. So what we have here is a volume integral, and we're summing the strain energy density. That involves stresses and strains, sigma and epsilon, respectively. And it also involves the gravitational potential. Now, if anyone has worked on variational principles previously at this point, particularly for the strain energy density, you're going to be thinking that I've gone completely nuts. Why would I be taking that on? Yeah, you got a point. I learned how to write some code to do this. It wouldn't get me all of the way, but it did help out. And so I definitely learned something about how to approach these problems in doing so. But that isn't the end of the story for the potential energy. So actually, really, all of the action is coming at the boundaries. And I'm just showing you the contribution from the upper surface of the ice here. And here we've got displacement of the upper surface, psi. There's also zeta, which is the lower surface displacement. And we have the applied stresses, tau, there as well on the surfaces. For the open water, we're going to do something similar. So just remember that I'm using the displacement potential phi, not the velocity potential. And then the kinetic energy should make sense. And then for the potential energy, I also have to include the pressure P. And we have the displacement of the free surface eta. And I'm just going to skip over the Lagrangian for the cavity because it's quite similar to the open ocean. Well, similar enough that I feel like I can skip over it. Another fun part, we're going to take small variations with respect to all of the unknowns. Okay, so for the open water, it's going to be, there are going to be variations in the potential phi, in the pressure P, in all the surfaces and all the applied stresses. And I denote those variations with deltas. And then we're going to find the first variation of the Lagrangian with those variations in. Okay, so that means that we're going to retain all the terms that are proportional to a variation and nothing else. So no higher orders or anything like that. And then you have the fun, lots of integration by parts. And I'm not going to present you with all the gore there. But what I will say, because I feel like I've been doing a bit of a disservice to this, is if you like algebra, and I mean algebra in its purest fashion, then this is fantastic. It is absolutely beautiful. The way that the physics drops out of these Lagrangians, of the first variations, is you know, I just didn't believe it until I saw it all coming out. Have I sold you? So simple examples here, right? So you end up getting these Laplacians coming out. You can see the Laplacian acting on phi and on something that I'm calling p hat. So p hat is just a combination of unknowns, and I'm going to end up solving for that instead of one of the other unknowns, and that is the thing that's going to derive the Bernoulli pressure. I won't go through those details. So we want to be able to take arbitrary variations and set the first variation to 0. So that means for arbitrary variations in P, then we're going to have the Laplacian of phi equal to 0. For the first variation of phi, then the Laplacian of p hat is going to be equal to 0, and so on and so forth. What I really want to do is focus on what's going on at the ice edge and the conditions that come out there. And in this case, we need to have two Lagrangians coming together, right? Because they both share that ice edge interface. And so we have to combine the first variations coming from both of them. So I'm giving you an example here those two terms in red share the first variation, delta tau 1, 1, put them together, and you get the condition that I'm showing below in blue. So that's just a continuity condition. And then similarly, we find some edge conditions that apply to the stress in the shelf, sigma, and couple to the pressure coming from the water. So the coupling comes from the normal stress, and then because we have a potential flow, we have no stress applied to the ice edge. So note that we no longer have a free edge. So far, we just use this variational principle to derive the governing equations for the problem. Now I want to use the variational principle to derive an approximation. So what I'm going to do is apply the standard thin plate assumption shown in red at the top there, where we specified the Z dependence of the ice shelf motions. Note the only unknown that we have is capital W, which depends only on X and T. And then all of the other unknowns in the problem are approximated indirectly. And so we put the approximation at the top there into our variational principle, and we derive the thin plate approximation. Sorry, I said something wrong there. Now the thin plate equation that's shown at the top. So it's almost the standard one. It does have that extra term with the rotational inertia J in there. And also note that as standard, we're getting coupling to the water through the phi term appearing there. Okay, so that's the fluid loading from below coming in. And we get these associated boundary conditions at the ice edge shown at the bottom there. And then we can say, well, they look kind of familiar. If I just go and cross out a bunch of terms like shown, then we go back to the standard thin plate approximation where we have a free edge. So there's no coupling in those ice edge conditions. All right, so now I'm going to show you some results in which we're comparing the new thin plate approximation that I just derived to the old one with no coupling at the ice edge. I've done a bit of a cheat here. For my own convenience, I've just dropped all of the terms involving the rotational inertia because I'm making use of some old code. So it's a partial test of the new approximation. But the crucial thing that it has is the coupling of the ice edge. And in fact, the only differences between what I'm going to show you, the new stuff and the old stuff, comes at the ice edge conditions. And I'll be showing you comparisons in terms of flexural strains, epsilon, at specified incoming wave periods, capital T. Okay, so what you see here are results for two different thicknesses, left and right, and two different periods, top and bottom. And okay, so overall what we find is that there is a great difference for the thicker ice on the top. Oh no, sorry, on the right, and for the lower periods, which are on the top. So the greatest difference is top right, where we have thicker ice and lower periods. And I guess this makes intuitive sense. But now we can start doing some more advanced things. So we can put in any approximation that we like and see what equations we generate. And the first thing that I've tried to do is to put in longitudinal waves through that term U highlighted at the top. So now I'm going to substitute that new approximation into my variational principle and see what it spits out. And what it gives me is a standard wave equation for capital U. And the important things here are that those longitudinal motions are not coupled to the flexural motions. So W doesn't appear in the wave equation for U, and there's also no coupling to the water through that equation, so phi doesn't appear. But we do get coupling. It comes from the ice edge conditions, and I've highlighted the relevant terms at the bottom. And here are some results that I generated recently. So I won't put my house on the fact that they're exact, but I do conserve energy, which is good. And I've sort of begun to reason to myself that they make sense. So these are the same results that you saw a couple of slides ago, but with new green curves added in there, which are the results for the approximation where I put the longitudinal waves in. So I'm just looking at the effect of the longitudinal waves on the flexural motions. So what you see is that the longitudinal waves have the greatest influence for the long wave periods. So I think that's quite interesting. I'm definitely running out of time here. So 20 minutes plus questions? 5 minutes of questions? Oh, basically, okay. I rushed through the last bit so I could have some questions. So we derived this new variational principle for thick floating ice. Makes no approximations from the outset. I've used it to generate some new approximations where the main newness of those approximations comes in the couplings at the ice edge. Now, still a lot to do, a lot of analysis of the results. I think the main thing is I need to keep on telling myself that I need to write this thing up. It's been going on for a long time. And there's other work that's beginning to appear in this area. In particular, I've highlighted this preprint from Eric Dunham's group at Stanford, and he was mentioned earlier on during the day. So this is a much more numerical way of treating this problem, and actually it would be great if you know, I could get together with him and actually see whether the approximations that I'm deriving hold up. But yeah, I'm kind of kicking myself that I didn't get this done earlier and get a citation out of this group. And there are other applications of this in the ice shelf context. Jordan was talking about the features in the ice shelf earlier on, having large effects on the waves that we were putting through there, particularly for the lower period swell regime. And I think it's going to be very important to test the thin plate approximation when you have large variations in the thickness of the shelf, for example. Okay, that's everything. Thanks for sticking with me. Got a few minutes for questions.
Thank you very much. First, I want to say I love your equations. Perfect.
I can show you many more.
Any questions?
Here we go. No.
Hi, I'm Mike Malin here. Thank you, Luke, and really wonderful work. Just to comment, doesn't this, aren't you, you know, criticizing all these people who, you know, use this wrong approximation, including Jordan's talk at the?
Sorry, which approximation?
I mean, you know, didn't Jordan's method also contain this funny this, you know, this non-submergent approximation?
No. Definitely, submergence is in there.
Okay, all right. Yeah.
I guess that's something I got right during my PhD.
Yeah. What about, because I know that the work that Balaji did, he had this, you know, essentially the finite element method is the it is the approximation with it is the variational principle, and he had some equation where he allowed one of the papers, he allowed that forcing at the edge, you know, from the physics. And he
is he online?
I noticed that
along to this.
and I know that he got some longitudinal waves starting to come down in the simulations. You could see when the wave hit, it kind of excited these compressive waves traveling through it.
Look, yeah, if he is online, then I hope he's going to speak up. But I did ask him a number of times about this.
Yeah, I think
Oh, hi.
sorry, Luke. Yeah, I'm here. Yeah, thanks for the talk, Luke. Yeah, I'm here. Yeah, I think we did this with the elasticity model, with the 2D elasticity one. but I think I didn't see much difference. Like I was actually surprised to see that much difference in one of your slides, like even the lower period regime. I think I may have to go back and look at the thing that we did.
It wasn't
2D
clear to me, Balaji, what conditions you applied at the edge. I know that you didn't have gravity in the ice shelf. So we have to do a bit of work in order to do a comparison.
Okay, yeah, I have to go back and look at it again. I remember coupling it with I think a similar kinematic condition that you had and a dynamic condition. I think I have to like go back and look at it again.
Okay. Thanks, Balaji.
Yep.
Any other questions?
Thank you very much. Thanks, Luke. This is training them. I'm kind of curious. First, can you possibly going back to your slides where you have this delta equations where you have this Laplacian to be zeros? There's two equations.
Yep.
Yeah.
Getting there. There we go.
Yeah, this one. Yeah. So I'm kind of curious that here how they are kind of orthogonized so that you have these two equations to be kind of independent. So
arbitrary variations.
yeah.
If
So
the
from
variations are arbitrary and independent, so that the delta p, delta phi are independent of one another. Okay. And that means the only way that you can set the first variation to zero is by having the Laplacian.
Yes, yes. I think I saw some other situations where they are possibly looking to second order of delta functions, which they have some sort of coupling behavior between these two. Yeah, I'm just kind of curious, like, are there any situations which maybe if you look into the high order cases, would that be leading to something more accurate?
I don't think so, because you derive all of the necessary equations from first order. So at best, you'd be an overdetermined system.
Yeah, sure.
Second order.
Yeah, thank you very much. I would be very interested to look into the details of this derivation. Yeah,
Okay,
thank you very much.
We have two questions online. Right? Roland, let's start with you.
Hi, I just wanted to address this last point. Is it perhaps relevant? The point is that's a Laplacian for p hat that couples it to phi, couples p and phi.
So I didn't really catch what Roland said there.
Roland, can you repeat
What I'm
your
pointing out
question?
is that while there are two Laplacians here, they're not Laplacians for the two independent variables. Laplacian of p hat is Laplacian of p and Laplacian of the second time derivative of phi. So it's not as though it's fallen into two independent problems.
We map to a new set of unknowns. P goes to p hat.
Isn't p hat is the one that couples them? So p hat has both.
Oh,
I was just trying to address the last question. It hasn't become a separate problem.
Because the variations are independent, then the variations in p and phi are independent, and p hat and phi are independent as well.
No, I understand the variational principles reasonably well. Just your last question seemed to be asking how you got to, I thought he was saying two separate equations. Perhaps I misunderstood.
Yeah, they are separate, yeah.
Yeah, they are, but if you're interested in pressure and phi, then they're coupled together by that second equation. It's not as though it's become a trivial problem of a pair of...
Oh, no. So they're coupled, yeah, of course. They're coupled together eventually So you solve for p hat plus boundary conditions, you end up deriving Bernoulli pressure. You feed that back in to other places, the remaining governing equations.
Okay, I'm going to stop this. Let's do one more question. We had Ellie raised a hand, right?
Yeah,
Ellie?
right. Sorry if my English is a bit rusty. It's pretty late here, but thanks, Luke, for your talk. It was really interesting. And well, my question was, you said that the stress-free boundary was applicable to sea ice since it's pretty thin. But I was wondering what would be the impact of including the submergence on sea ice on the stress field.
Class?
Probably not much.
Yeah, okay. So
but I think from my results earlier, where you see the thinner ice, right, it's still very thick for sea ice. Yeah, you see the effect of those extra terms at the edge becoming negligible pretty quickly.
okay, yeah. So sorry, there was someone like making noise in the Zoom, but I understand that it wouldn't change a lot.
Yeah.
Great, thanks.
Okay, thanks, Ellie.
Okay, let's then look again.